Now here is my system. The VGS, if you look at here, the VGS is this part of what? So I will isolate the loop that has the VGS value. Now, since this is the entire current is going to, the entire signals and currents is going to go into here, into the VG. So that RG is extremely huge. So it will be seen in the analysis as a wire, as a short circuit, just a short wire. So this will become like a wire right there. So the entire thing is going to be what? Entire signal will be transferred into the gate point of the FET. So this, in order for us to get the network curve for that fixed bias, it's going to look like as if I have right here. So now VGS, this is my G and this is my S, and it will look like what? It will look like VGS equal to what? VGS. So here is my loop right there. This is extremely huge, so it will act like a short circuit. So now you get that VGG, and it seems like the VGS is equivalent to negative VGG. Or even if you consider this is like a diode or any terminal VGS, you would say by using the loop VGS plus VGG equal to 0. The voltage drop across a loop is 0. So if I have a voltage levels right here, or if I even consider this like that, right? So now that VGS levels, I start to the analysis get a reference VGS plus VGG equal to 0. So you could say VGS plus VGG equal to 0. Therefore, VGS equal to minus VGG. So the network curve is, this is a constant. It's a battery, isn't it? That's a plus minus. That's your battery. So it's a fixed value. And you know VGS is on the x-axis, isn't it? VGS is the x-axis for us in the analysis. So as if mathematically, as if you have something like x equal minus k, isn't it? So when x equal minus k, what is this for us, x equal minus k? What kind of a curve x equal minus k represent? If I tell you draw x equal 5, how do you draw x equal 5?
The y is 0. 5 and 1 over.
X equal 5.
It's parallel to the y-axis.
Parallel to the y-axis, so it's a vertical line. X equal minus 7, vertical line to the left, isn't it? So now, the network curve for fixed bias, VGS equal minus VGG, and VGG is a constant. So it will look somewhere what? It will look somewhere right here. So now, that VGS or that battery, or you see, on the intersection point, That's your Q value. So now, from the Q, I will read my what? I will read my VGS and ID. Obviously, VGS is my value, isn't it? Then you go and read your ID on the other side. Once you come up with that value of ID, then we go back again to the circuit analysis to find the rest of the terminal values. So that's a very systematic approach. You need to understand it. Once you get the Q, forget it. It's done. Problem is done. It's a matter of time to develop the rest of the equations. Okay, so you understand for fixed bias, the network equations. The network equation is VGS equal to minus VGG. Obviously, that voltage level VGG cannot exceed what? VP, right? And will not go beyond 0, correct? Because if you imagine this curve, if you imagine the network is moving left to right, then it has a limitation. To the left, it will not go beyond VP, and to the right, it will not go beyond what? 0. Because every time you move this, the Q value what? Shift up and down. And that's the beauty about this feature. The beauty about the feature is this will allow us to think of how to troubleshoot a network or how to meet the customer's demand for particular current level. So if I'm here, so how to change the Q value for what? Particular levels of voltage and current, because you could see here, if that point moves up here, by simply changing the voltage level, VGG, so if I make it equal to -1, this will, let's say, move up here. So now the Q goes up. When the Q goes up, then more current, right? More current. So now I could keep this in mind that anytime I need to meet particular ID value, I could think about what? Changing the network curve. One possibilities. So I could meet customers' demand for particular current or voltage if I just think of dynamically moving this Q value. The things to keep in mind, you are going to analyze circuit. One question is on the exam, always circuit analysis. The rest is basic computations. Okay, but I need to see that you do understand some levels of circuit analysis. Okay, once the network curve is found, the blue one is my network, the red one is my chip. Superimpose both of them on the same axes, then the intersection point is the Q value. When the Q value is found, now I go to my terminal. Now the terminal, by looking at this, you could see that my Vs is equal to, what will be my Vs equal? Vs?
IDRS?
No, Vs. Voltage. This is the circuit, that's Vs. It's connected to ground. So I know automatically that this level is 0. So now my Vs is 0. And so first things to remember from this circuit analysis is you're not deriving anything. You're looking at the circuit. So Vs is 0. Now I need what? The next is Vg. Next is Vg. Now you know that Vgs equal to Vg minus Vs, right? You know that from the Vg, voltage difference, Vgs equal to Vg minus Vs in DC. Oh, voltage difference.
Yeah.
So now if Vs is 0, if this is 0 according to this, then Vg equal to
VGS.
Vgs. And I know that Vgs equal to negative V, negative VGG. Negative VGG. You follow? Okay, so now I found what? I found Vs, I found Vg. Now I need Vd. Now, Vd, you know that Vds equal to Vd minus Vs, right? If Vs is 0, right? If Vs is 0,
Then VDS equals
then Vd equal to
VDS.
Vd equal to Vds. In other words, at this point, do you agree with me that if this is 0, this is Vds, right? That's Vds.
Correct.
So if Vs is 0, therefore Vd equal to Vds, right? At this point, and at this point, Vd equal to what? Vdd minus ID
RD.
RD. But that ID is the IDQ that you found. That's the whole idea of the analysis. That once you find the VGSQ, and once you find the Q, which is the VGSQ and the IDQ, that levels right here is your IDQ. So this will make this equal VD at this point equal to what? Equal to this voltage minus whatever it dropped. So it's equal to VDD minus V RD, isn't it? Minus V RD. And we know that VRD equal to ID, the current, times the resistive element. So it's equal to IDQ times RD. That will make the equations equal to VDD minus IDQ RD. Vs is 0 from the analysis, from the terminal. Vg, if I look at this, I could see that my Vg will what? Meet the minus VGG, or we know that VGS is Vg minus Vs. Therefore, you could claim that VGS equal to minus VGG from the network. Right? So we already told you. This is VGS equal to VG minus VS. This is 0, right?
Yeah.
This is 0. So that's my VG that I'm looking for. It's equal to VGS, and I know from my network it's equal to minus VGG. Not a high levels of analysis, or something based on typical equations and DC analysis. So we could put the equations right here. Your VGS equal to minus VGG, that's your network curve. Your VS is 0. Your VG equal to minus VGG, and your VD equal to VDD minus IDQ RD, and if I need then my VDS, because here if you look at this we need everything, VG, VS, VD and VDS. So now I could claim that VDS equal to VD, right?
Yes.
VD, which is the same equation, equal to VDD minus IDQ RD, Arabim, Arab. Okay, very systematic procedures. Okay, we take a problem and we look into some kind of analysis. Here you go. Suppose I'll change value. Say this is 16 volt, and I'm gonna. I'll use mine. We use those values on the board. Suppose this is 16 volt, and say this is 3.0 K, and this is 1.5 meg. Assume the battery is at battery is a 3 volt, but because the potential is what? Reverse, right? So we normally write minus 3 volt. I should put 3 volt, but the potentials, it's reverse, right? So normally you probably see it like this, 3 volt.
IDSS?
Or you could put minus a 3 if you want. The system should be, that's from the manufacturer perspective. You know that these IDSS, so let me put some values. Suppose IDSS equal to 12 milliamp, VP equal minus 8 volt, minus 8 volt. Try to have an index card, try to, whatever, I don't know how's your styles by now. I mean, about to graduate, if you have not yet developed a style, we got a problem, especially as an engineers or technologists. So styles and getting a good note. Good note, I mean, you write whatever you want, but at least the standard equations, you create some kind of a reference manuals for yourself. No matter what you do in the field, everybody, when we say fixed bias, that's the only thing that comes in our mind. This. So this is right now. If I'm doing here fixed, bias, you know that it's going to be what? An RG with a VGG level with a battery, correct? So a suggestion might come in, from an engineer. Look, it's use the fixed bias to amplify the signals according to your mind has to go directly on the what does it represent, right? So as an engineers and technologists, we don't, if you work for a company, we normally don't challenge each other. Means, you're an engineer, I'm an engineer, we both graduated, this, that, that's not a place for this personal, right? But certainly if you're working with us on a team, we don't have time to explain to you what is a fixed bias and what is this and what is that. So you automatically don't belong to the team. It might have an unbelievable, effect on you. Couple of a project, and if the team continue to explain to you, or we're spending time trying to tell you or show you the obvious, we got a problem. You don't feel it until what? Until the papers on your personal file say, well, I need to strengthen his knowledge. Need to strengthen his knowledge, forget about it. It means one more project, then you're out. You're out. You don't belong there. You need to. So just graduating and I have a degree, hold that thought on that. Once the ultimate test is when we out there and so on. I got so many, lot of time projects come to us from engineers for mathematical purpose. Believe me, for mathematical purpose. Those who's taking it with me, applied calculus, you'll see a lot of this. So suppose what would be, this is the criteria. Now we analyze the circuit for all. The first step is finding the Q, right? Finding the Q, and that's the easiest of the biasing because the network curve VGS is actually equal to the battery. So let's put, of course each one will have his own graphical papers. Let's do the chip curve for this. Chip curve IDSS is a 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Then 1, 2, 3, 4, 5, 6, 7, 8, right? For VP. Half of the third point, half of this. What did I have? VP. Right, negative 8. Now, half of this, which is 4. 1, 2, 3, 4. And that's going to meet what? Quarter of this. 12 over 4, which is 3. 1, 2, 3. You may go like this. So this way, you establish what? You establish that Q, and then you go with your chip curve. Now, the network curve, VGS equal minus VGG, and VGG is equal to minus. 2 minus is 3, so 1, 2, 3, and we will draw what? We will draw our line. Okay, so this is my negative 3 volt. This is my negative 4. The red line intersecting the blue line at this point. Now I read my value. That looks like a little bit what? Above. So that's my Q. How do I want you to put, yes?
You get the negative 3.
It's VGS equal, the network curve, VGS equal minus VGG. And from the example, VGG is negative 3, right? Negative 3.
Oh, okay.
So I draw this network, VGS equal minus, VGG equal minus 3.0 of a volt. So that's a vertical line, correct? So now I could say this is IDQ 1, 2, 3, 4, 4 point, let's say 4.2, right? You use your own interpretations. This is a graphical approach. Intuitions into this, you know, it's below the 4, it's not 4.5, correct? So we're not asking you to be 100% accurate because this is a graphical, right? There is an about 6% error anyway because of this vision, relying on the visions. So now, suppose it's about 4.2 according to what I have, right? Even though I could argue it's about 4, but it's a little bit above. Above, I say 4.2 milliamp, and my IDQ, see what I'm doing? My VGSQ, negative 3 volt. So though my Q value, always put the Q value in this corner, right there. So the Q is what? Is negative 3.0, comma 4.2. So we know that this way we know that that's ID.
So I got that 4.2 again?
I'm sorry. I read it. I'm reading.
Oh, okay.
I'm reading. 1, 2, 3, 4, 5. I said, well, I'm 4.2. You follow me? My own. On your paper, you may have a different. Whatever you have on paper. Whatever you have on paper. Okay, because that's the whole idea. It's going to be a different Q value. In your lab on Thursday, you will continue soldering your piece, but you will also practice the graphical analysis for multiple network. So this way you get more into this. Okay, so now I finished 80% of the problem. I move into the analysis. So the analysis on this side will say, we know that Vs is 0. Even though if you tell me I memorize it, okay, that's the whole idea. I make it quicker. But from the circuit, you know Vs is what? Going directly to ground. So this has a 0 potentials. So if Vs has a 0 potential, VD, so Vs is 0. I'll do VG because it's equal to minus VGG, which is minus 3.0 volt, right? Now, in other words, the battery is a 3. But because it's reversed, so it's minus 3, or in other words, that VG sees what? That negative values of the battery. So it's a minus VGG. So 1, 2, next is what? Well, VD equal to VDD minus IDQ RD. VDD equal to what? What did I say? 16 minus IDQ 4.2 times 3.0K. So this is a milli. With the K becomes a voltage, right? Cancels each other. So this becomes a volt network. So that becomes 16 minus
12.6.
That's a volt, and the answer is
3.4.
3.4. That's it. You finished. That's how I want the work. On the exam, on the final, in the field, at the technical work, this is what you're supposed to have at all times. Okay, so that's the voltage levels, the voltage terminals, and VD. Then I could claim that what? VDS equal to what? VD minus VS. Therefore, it's equal to VD 3.4 minus
0.
0, which is 3.4 over 4. Now, here is, so that's the circuit analysis. Where is the technology aspect of this? The engineering. This is engineering. That's the job of an engineer. Break down,
Yes.
analyze, use equation, bada bing, all set. Now, a question could be, if I have, based on what I have told you, there's two levels of technical applications. The first level is what? What's the first level? What did I say?
Practical.
What is it?
Practical.
Analyze multiple stages. And the second one is
Meet the manufacturer investment.
determine particular
Q.
Q values, right? So I suppose I need, here is system 1. System 2. Now if I need a particular current level, I want ID equal to 5.8 milliamp. How do I, and I already have a network, right? I already have a network that produces what? IDQ equal 4.2 milliamp, right? This is the customers. The customers have a system, and that system requires 5 milliamp. I want 5 milliamp for the ID. So now I have already this that has what? Well, it's from 0 to 12 milliamp, so I know I could use this network. All I need is to adjust my work for, what does the customer want? 5.8 milliamp. I go to my circuit. So what value, question, so this is part 1 of the analysis, terminal analysis. This is the terminal analysis, part 1. Part 2, what would you adjust? How would you adjust the network to produce a 5.8
Change the value of R.
milliamp? Phase 1 is the Q value and what? And terminals analysis, terminals value. Terminals, I will put right here. Terminals value. So we got it. Part 2, how would you adjust this network? Or what would you adjust to produce 5.8 milliamp? Technician's perspective, they take the circuit to the lab, right? And they just build it, and they continue changing certain voltage level or certain component until the amp meter reads 5.8. I have to take out this, I'll strip this and put what? An amp meters in series with the network, and then I start changing. God only knows which component is you're going to change, right? Until you come up with this. Some people will jump and change the FET not knowing. No, they don't have that knowledge base that you have. Knowledge base is, now I know this is produces up to 12. I mean, they might give you, the customer might give you the design anyway, and saying, look, the design is already like a 2-port network, like that. Signal in, signal out. But it's already packaged, installed. And it has the specifications right there. So it's a 2-port network. The specification is minus 3.0, 4.2. This is that's what the block shows mapped on this. This means what? That's this network. This system produces 4.2 milliamp. Now I need to adjust it to 5 point. Why should I go and purchase another 2-port network, right? They're built in. You buy them. You buy those 2-port networks. They come like in a filter, like a filtered format. I don't know if you've seen these. These are just like the coupler. I'll show you if you operate some of them. They have two. They're already packaged, and the spec is given. So now, why should I go and buy another one? I'll open this, and I'll check what do I need to adjust. The adjustment is, one of the adjustment is you might end up, if the customer's both current level or voltage level according to your theories does not meet the JFET, you might have to take out the JFET and put MOSFET and so on. But here I have already my design, my blueprint. I need 5.8. 1, 2, 3, 4, 5, right? 5.8. So suppose that's what still graphical, right? That's what the customer wants. 5.8. Then I go draw a line extended where I hit the chip curve. I read about -2, right? I read, and that's my. No, that's my VGG right now.
Mm-hmm.
So now I don't have to change anything inside this network. Opening this network and playing around with it and try to change resistors, you don't need, because this is the VGG, right? And VGG is external, it's just the battery. So I tell the customer, take out this voltage level and put 2-volt battery, right? Finish the problem. And then you got people opening this 2-port network, trying to change the resistor. You have resistors, capacitors, you have this. Now, which one I gotta change? They start playing around with it. We got a problem. The worst case scenario is technicians trying to change the capacitor. The capacitor in the design have nothing to do with the work. Because the capacitors, as I showed you, its objective is only coupling, right? It's just to pull the signal to pull the signal and push it toward what? Toward the gate. And you got people trying to change the capacitor. Oh my God, I'm not getting any amplitude change. They put the ammeter and they start what? They take out the capacitor and they put variable capacitors and they start changing and they don't see anything. It's not going to change.
Well, Professor, then why would a company assign a project to a technician if this is the route they're going to go by changing pieces?
I mean, this is the worst case scenario for the engineer. Give it to the technician.
Right, but I would assume that at least a technician would have this type of background to at least acknowledge.
You
Not always.
would hope. you would wish, you would hope, because normally knowledge-based technicians is based on what? Normally based on the physical, physical features of the circuit. You give them the circuit, they build it, they start reading and stuff. But they're not. Their mind is not set on what? On the boundaries of the values. They're set on based on the instrumentations. Voltage level, current level, I change, what do I see? Can I use this to solve a problem? You certainly could, but it will take you a little bit of time. It will take more time. I mean, this is the easiest of all. But even though it's the easiest, some technician might go on to a different route, opening what? Opening the system and trying to change the resistive element here, resistive element here. No, they don't have that knowledge. Check. Okay? So, I go with this directly and it gives me what? So any voltage level, any current level I need, I could do it from 0 to 12 milliamp without changing the FET, right?
Yeah.
Without changing the FET. Normally is the current level that you're interested in. But if you have the current and you want the voltage, we could also do this. It's not a big deal. So we got the current level. Here is the voltage. You read it from the graph. Now let's see how, if you're using the Shockley's equations, for example, you know that ID equal to
IDSS.
1 minus.
VGS over D squared.
So how good are we in this graphical analysis? So we go with ID, that's 12, 1 minus what?
The -2.
That's the one that you're trying to find, yes?
Oh,
So this is a
VGS,
minus, VGS is minus VGG. So this is a minus
3.
over
8.
minus
Minus 8
8.
square.
Negative over negative is positive. 3 over 8 is what?
0.375.
Okay, subtract it from 1. Minus 1.
Minus
How much?
0.65.
0.62.
Square it.
Uh, 0.390.
And multiply it by 12.
4.68.
4.68. What did I get?
We got
4.2 graphically, right? 4.2. That's my scales and my work and so on. So if I go with 4.2 divided by 4.68 equal, right? Equal time 100 minus 100. So I'm about like 10. My error here is 10%. I'm like a 10% error. 6% is the acceptable. When we say 6%, because I have to give you the curve. Then 6% is fine. Here I'm saying this is 1, this is 2. I could have what? I could have moved a little bit further because it's only 3 points, right?
Yes.
So that's my graphical work. So if the customer wants 5.8, what would be, in this case, the Q value if I want to do it mathematically? So 5.8 equal to 12, 1 minus
VGS.
VGS. I'm looking for, right?
Yes.
VGS over
-8
-8
squared.
squared. So that gives us what? We solve for VGS from here. Okay, so even if you put VGS equal to what? VG minus VGG, so that turns into 5.8 equal 12, 1,
Plus.
1 minus, right? VGG over negative cancel square. Then you could say 5.8 divided by 12 equal to 1 minus over 8 squared. You take the square root of both sides. So square root, what's 5.8 divided by 12? 5.8 divided by 12 equal, you take the square root, it gives you 0.695, right? Right, and that gives you what? 1 minus VGG over 8. So that goes to this side, minus 1. That gives us minus 0.3, right? 35 equal to minus VGG over 8. You multiply this by 8 equal is about 2 point, so VGG will come up to about what? About 2.4. But in my graph is higher, 2.1, right? You see it? So here I could claim that we did 5.8. My graph will show me let's say 2.2 or 2.1. In reality, it should be what?
1.4.
So because this is VGG, the potential will be minus 2.4. You follow me? Oh. That gives you, so it's equal to 2.4 as a battery. But when you put it inside the circuit, it will be, because of the potential, you're going to shift it, right? That will be minus. So VGG equal minus 2.4, and I'm getting 2.1. 2.1, for example, 2.1 divided by 2.4 multiplied by 100%, I'm still under almost 10%, the same error that I got, right? From the first. You follow me?